Yeah?
What's the bottom line? Is it dead or alive?
I don't know. Dead for sure. Maybe it may be alive.
Possibly alive.
I can vouch for the dead part. For the alive part, we will see.
Hi everyone, welcome to the after lunch session. The first talk will be by Muhittin Mungan, who will be talking about self-organization and memory in a randomly driven disorder system, dead or possibly alive. Muhittin, go ahead.
Well, thank you very much. Thanks for the organizers for having me here in India. It's wonderful to be back. In fact, the first time ever I came to India, and this is the second time, it was in 2018. This was a workshop at ICTS that Shri and colleagues organized. This was entropy, order, and information in soft matter. And in some sense, the classification of these ideas that I'm going to present, started out there. Around that conference, there was a transition, and it led to my getting interested and learning about amorphous solids. And this is kind of, maybe if you like, the seeds of this have been planted in ICTS about in 2018. Okay, so with that, let me give the motivation for the talk. Here is a pair of shoes. These are, in fact, my shoes. I'm obsessive compulsive. I like to buy the same brand. So on the right is a brand new one, never broken in. The one on the left is one that I've been wearing for 2 years. And you clearly see differences, right? So by walking, you basically deform the shoes, and the shoe adapts to your lifestyle. So you're imprinting a memory of, how you walk, whether you jump up and down, whatever you do. So suppose, maybe Itamar, good friend of mine, he wants to borrow my shoes. We have the same shoe size. Okay, but okay, someone wants to borrow the shoe, I give them to him, and of course for him the shoe doesn't feel right, although it's the same shoe size, so it's broken in. He says, very nice, here they are, take them back, and I start to wear them again, and they start to feel bad again. So this is an elementary sense where a system adapts to a sort of fluctuating environment, and this is a very elementary form of memory, and this is kind of what I'm interested in. And somehow, the shoe adapting to your quirkiness is a process of self-organization. And so, can random driving of a disordered system lead to self-organization and memory formation is the question of this talk. And of course, we will turn to our most favorite disordered system, a disordered shared amorphous solid. And so, with that, let me first give you some reviews. There's, of course, the review by Keim, Paulsen, Zeravci, Sastry, and Nagel. From 2019. Shri and I wrote something for the soft matter roadmap. Then there was a review by Paulsen and Keim in Annual Review of Condensed Matter Physics. And sort of a subset of what the superset of what I'm going to talk about is actually in this review that we wrote together with Shri, Eric Clement, and Damien Vandenbroek, which is self-organization, memory, and learning from driven disordered systems to living matter. And this will appear in annual reviews next year in March. But there's an archive version out there. Okay, so we all know about this. This is sort of like an exemplary amorphous solid, a binary, 2D binary mixture of Lennard-Jones particles, and I'm considering them under athermal quasi-static shear, AQS. Anael and Craig introduced this. And so, when you look at now the stress response under applied shear, you see that the stress initially builds up. It crosses over into some stochastic steady state. That's the yielding transition. But you see the buildup, and also in the steady state, has two regimes. There's a regime where the stress just changes more or less continuously, punctuated by stress drops. So the continuous part is what we call the elastic response. The stress drops are plastic events. And this is basically mechanical instabilities because we are at zero temperature and we are rate independent. Mechanical instabilities that set in lead to a very, very fast relaxation process. And that typically has this SLB type quadrupolar displacement of particles. Some particles start to rush out under the applied shear strain. Some move in. This gives rise to long range redistribution of elastic stresses. Now, being a physicist, you want to simplify this, so you want to coarse-grain the system, and that naturally leads you to elastoplastic models. So here, this is going to be a very simple elastoplastic model. Again, I coarse-grain this 2D system into a lattice of cells. Ij is the index of a plaquette. And each plaquette basically has a yielding behavior under local strains and stresses. This is what I'm showing you here. So what you see here is the local stress in this plaquette Ij. It's composed out of the external stress. This is all scalar. This is not tensorial, plus an elastic stress, okay? And as you increase the loading, you increase the external stress. So this system moves towards an instability. This means that the cell will yield. There will be a jump to a next local elastic branch. Now this instability will give rise to a redistribution of these elastic stresses, okay, local elastic stresses in this quadrupole manner. So some other cells will be moving closer to their thresholds or away from their thresholds or even across. An avalanche will set in, and when the dust settles, I have a new configuration. What is sort of a little bit special about this model, this is a standard elastoplastic model, is that we basically associate with each cell a stack of local elastic branches. So, if this cell is in the elastic branch L and it becomes unstable, it gets into the branch L+1, which has its own thresholds. But if it gets unstable here, it returns again to L. So locally, as I get unstable in the forward direction, these local elastic branches go from this to this, and then, in the reverse, they go here. So I have a local reversibility in there. Okay. However, that doesn't mean that things have to be reversible at the global scale. Now, at the global scale, I apply a strain, and there's a stress, in each of these local, in each of these cells. So in each of the cells, the local stress has some value. I can now keep on increasing the strain or the stress until the first cell becomes unstable. So in one cell, it reaches one of these sort of instabilities. It says, wait, I need to relax. So it relaxes, it causes redistributions of other cells, maybe that may also relax. And when the dust is settled, you land now in this global elastic branch. Now, if you reverse sort of increasing the shear, if you're now reducing the shear, maybe then there's again in the system another cell says, wait, I need to relax. So you relax it, and the system may turn into a completely different elastic branch. Rather than returning to A from where it came, it returns to B, because the events that made this transition possible were triggered typically by some completely unrelated or less related cells from the cell that triggered the return transition. So upshot, although locally you have reversibility of the elastic branches, globally you don't have to, and in this model this is sort of generally you will not have, okay? So we have sort of talked about this, and now we can do what many people in this room have done. You basically take an amorphous solid or its elastoplastic version, you train it. And the train is you take a poorly annealed version glass of this, you subject it to oscillatory shear at some training amplitude T for a number of cycles, and as a result of this, you get what we call the trained state here. And what you do then is since we are sort of theorists or simulation people, we take copies of these T's, and for each T, we apply a single cycle of a variable amplitude epsilon r. So one copy gets one epsilon, another one gets another readout amplitude. And we basically compare the configuration that was reached after this readout cycle to the one that was trained, and we have a distance, mean square displacement, or something of that form, and we see how that distance between T and R depends on epsilon r. And now if you don't train the system, and this is results by Shri and collaborators, if you don't train the system, then you haven't done anything, this is the fresh class, then as you increase the readout amplitude to be used here, the distance between T and R just goes up. Now if you trained it for 2 cycles, this is the green curve, it develops a shoulder here. The training amplitude is 6% strain, so that's indicated here. If you train for 4 cycles, you get a little bit of a clearer shoulder. After 10, you get a clear dip here, and then it rises up very, very sharply. So in some sense, this is sort of, this is a standard probing for memory in the system. Somehow the training has been encoded into the mechanical features that you can retrieve by applying sort of, a cyclic shear. And this has been observed experimentally. For example, Nathan and his students have sort of verified this in for polystyrene particles at an oil-water interface. And this is sort of, the readout for 2 different strain amplitudes of 3 and 4%. And you see again, at the point where the readout matches the training, there is a dip in the MSD, and followed by a really sharp rise of the displacement. And this is from this model that I just described you. For now a whole range of training amplitudes, you see these red colors indicate the training amplitude. Let's focus on this one here, for example. So for readout amplitudes less than the train amplitude, the MSD increases, comes down, reaches actually a minimum close to 0 at the training amplitude when readout and training matches, and then it shoots up. Okay, so this is fine. But you could ask, when I walk on my shoe, I'm not really doing periodic shearing, especially not when I'm giving a talk. I'm jumping up and down and doing other things. So could I get the same thing using some form of random deformation instead of oscillatory deformation. And sort of, the simplest thing is, as a training, we will consider a random walk along the strain axis with fixed steps that I will fix once and for all. With the probability 1/2, I make a step to the left and right. And I will have two reflecting boundaries, at epsilon max and minus epsilon max, and epsilon max is now sort of my training amplitude. And what I will do is I will basically randomly deform the system in this protocol, and the cycle, I will start out again with some purely annealed sample at position O. I wait until my random walk hits one of these two boundaries for the first time, say here. That will then define my direction of positive shear. Then I wait until it hits the other boundary, and then I wait until I return to 0 for the first time, and that's going to be my first random cycle. And I will keep on doing this for, say, 20 cycles, and then I will have, again, my trained state T. So this is then my trained state T that I have here. And again, I perform a readout with variable amplitude, and I want to see what the distance between T and R is, at fixed epsilon max and varying epsilon R. And this is what it is. So this is now shown for different training amplitudes, which are these vertical lines. And you see pretty much the same phenomenology. There is a kink, at the readout amplitude when it matches the training amplitude, but beyond that, there's a sharp rise. Now you can put a twist to this, and you can say, so far, so take home one, this self-organization happens under random driving. It doesn't have to be, cyclic shear in order to get sort of these readouts, okay? Now you will add another twist to this, and I will say, look, my readout will actually not consist out of a single cycle, but I will add a second cycle. So far, I've basically measured the distance between T and R. Now I'm also going to measure the distance between R and R2, okay? So I will see how the distance between the state at the end of the first and the second cycle changes as a function of the readout amplitude. And this is what you see here. Again, for the same training amplitudes that I had shown you here. Okay, now you see for the 3%, it is 0 and then shoots up. For a little larger training, it's 0 and shoots up, and then gradually, this abrupt jump basically gets more smooth. But you see, you can kind of read out where it has been trained. Okay, so this means that this gives you some insight into what this random driving is doing, because you see, the first cycle basically gets you somewhere. So, let's be at 0.2. Maybe this is the training amplitude. This one, the first cycle gets you a distance away, from your trained state. The second cycle returns you to there. And this is regardless of where the first cycle has gotten you, as long as the amplitude was sort of less than what you had trained. So this system, although it has been driven randomly, has acquired a high degree of mechanical reversibility. And which I mean is that these localized plastic rearrangements can basically be repeatedly, initially, they can be done and they can be undone. Okay? And maybe since, Mahesh had been talking about this, and maybe even Gilles is around here. No, Gilles is there. Oh yeah, hey Gilles, okay. So you see, this is an elastoplastic model, but if this was a random field Ising model, okay, this, with ferromagnetic interactions, okay, what you would see is this. There would be no signal. I mean, no matter how you prepared your Ising magnet, you cycle it twice on the magnetic field, okay, and you measure the spin configuration, okay. It's at the end of the first cycle, you basically are locked in a limit cycle, and the second one is bound to get you there. So it's completely flat. And in the Price-Zag model that Mahesh was talking, this would also be the case, but there you don't have any interactions. So the fact that this rises up here, okay, has to do with the fact that if you want to talk Ising language, that there are antiferromagnetic interactions in there, or if you want to talk amorphous solid, that, the stresses that are basically are imposed on the system when something yields are not only making the rest of the system more susceptible to swim flips, but they can also stabilize them. That's the big difference, and that gives rise to this sort of, and that is, I think, in this language, which is sort of, there's a certain amount of frustration that is coming from this quadrupolar nature of stress redistributions. Good, so this is the phenomenology. Still the phenomenology. Ah, yeah. And, this was for an elastoplastic model. In the meantime, Ronnie, who has a poster on this, and a student of Shmarajit, has verified the same picture for an atomistic simulation of a Cobb-Anderson glass, and he has a poster. And again, this two-cycle gets 0, rises. So we basically recover the phenomenology in a more realistic model of a glass former. Good. So with that, how much time do I have? Okay, good. So then let me recap what we have. So the mechanical annealing by deterministic or random shear leads to self-organization into a state of high plastic reversible, because the first cycle gets you somewhere, but the second cycle gets you back regardless of where you're gone, as long as you're not shearing it well beyond what you've trained for, okay? This is emergent. It was not in the initial train. It was not in the initial state. It came out of this random training that we've been doing. And this reversibility can be probed by various readout protocols. So how can we understand it? How generic is this? And, do this sort of frustration and maybe a large number of degrees of freedom suffice? And, the way I want to approach it is, these phenomena emerge already under athermal quasi-static driving. The driving is low dimensional. In our case, it's just a one parameter deformation, the shear strain along a fixed plane. And so this response can be represented by transition graphs. So I will show you how these graphs are constructed. And I will show you what these graphs can tell us in terms of describing the phenomenology that I've just presented to you. So here, this is the idea. We are athermal quasi-static, so my energy is just purely potential energy. So it will depend in particular on the configuration of the particles as well as my scalar deformation parameter, which is the shear strain. So, if I want to have a stable configuration, first of all, the gradient of this potential energy with respect to coordinates has to be 0. The Hessian has to be positive definite. So suppose I found a solution here. So this is my configuration axis, and this is my deformation parameter. Now, if I change the strain by a little bit, I will get a nearby solution. In fact, this condition with stability will basically implicitly define the function of the deformation of all of these particles as a function of the deformation parameter. This is just the implicit function theorem in mathematics in disguise. And this will continue until the Hessian develops for the first time a 0 eigenvalue, which means that, if here all of the eigenvalues are positive, I increase the strain, I move along this, the configurations adjust elastically. At this point, for the first time, I have a 0 eigenvalue. If I don't cross it, I can return along the same path, and then in the reverse, I have another 0 eigenvalue appearing here. So in between here, the system responds completely elastically to my applied strain. At these 2 points, I have an instability, so there will be a relaxation mechanism at constant strain, leading to another of these curves. These are elastic branches, leading to another elastic branch. And this process I can represent in terms of a graph. What I do is I say, look, this is all elastic. I will take this elastic branch and collapse it to a single vertex. That's what I call the mesostate. And I can leave this elastic branch only through 2 exits, namely either through the upper instability or the lower instability. So these are the 2 areas that go around. And since upper is different from lower, upper will be colored in the dark color, and lower will be colored in the light color. So I go from branch A to branch B, and from branch A to C, depending on which of the thresholds I basically trigger. Okay? And of course, I don't need to, and these transitions are exactly this sort of, localized, plastic events or soft spots. Of course, I don't need to stop there. So I could then ask, what happens then from this? Where do you go when you go from these endpoints? And I can basically use standard molecular dynamics simulations, to basically follow these instabilities. This is what I'm doing. This instability leads me there. Then, I trigger the next. Where does it lead me? So follow the instabilities. Where does it get you? And this is...
Like if branch A is closer to B than C, then it's more likely that it will.
But this axis is completely fictional. There's no distance on there. Okay, yeah. Okay. So now this is what you could do basically by sampling a transition graph. You start with, this is from a system of 1024 particles 2D of a system that I think with a potential that you and Edan had introduced, that Ido has been using. So 1024 particles, this is my initial glass. I know from this poorly annealed, I have 2 transitions, and I've shown them, and the triangle means I don't know where they go yet, okay? But I can basically go here, trigger the instability there, or here, and this will be basically, this is right now generation 1, and this one goes to here, this one goes to here. You see, this one goes to the same one, okay? And this one goes to another one. This is generation 2. And then I can do the same thing on these triangles. You see, every time I have a triangle, I have 2 unresolved transitions which I need to resolve. So I can continue, and I have a way to check whether I get back to a same vertex or not. We can talk if you want to do this, but this can be done. And so this is at generation 6, and you see, this is at generation 10, and then, I can fast forward. This is what it looks at generation 25. And you can go well beyond that, but this is good enough for this. So this was my initial state. you see at generation 25, with every sort of mesostate, I have two choices. Do I trigger the lower or the upper transition, okay? If I go for 26 generations, I have 25 generations, I have something like 2 to the 26 different choices of, up-down transitions. This comes to 6 times 10 to the 7, actually 6 crow, as I learned this. Okay, this is a number of 6 crow states. Okay, which is far larger than the number of 1,416 states that are sitting in this graph. Which means that many of these up-down sequences, okay, lead to the same state. So there's a high, already from this you see there's a high reversibility in this graph. Okay. And so the other thing is, this is sort of an alternative way of looking at how the system responds in the deformations. Because you start out with this graph, and any deformation path is a path on this graph, okay? So if you just do uniform shear, you just go along the gray arrows and you keep on going. So this means the yielding transition is somewhere in this graph. The irreversibility transition are all somewhere on this graph, and they are encoded in the graph topology. And the topology gives you, bottlenecks. In order to get to this part, there's only 2 transitions that give you this. You see tree-like structures. Okay, so this is an alternative way, kind of like a phase space approach in classical mechanics. Where you don't look at individual trajectories, but you look at the flow of trajectories in phase space, and you look at their geometry. This is sort of a very similar idea, which gives you a different perspective on the system. Okay, so that's that. So deformation histories are basically mapped onto the graph.
So why is this graph a tree? Like, why aren't there any cycles or anything like that?
Well, there are cycles. For example, you see, if I go here, I go up and down, I strain up, down, and then I land in this cycle.
I see, okay.
Okay, there are cycles. You see, I'm not going to tell you that this graph makes this picture a lot easier because, the response of an amorphous solid is complex, and that complexity does not evaporate, okay? But it is now transferred into the topology of the graph, which in my opinion is a much easier thing, or, at least to my taste, a much easier thing to deal with than with a system of, thousands of degrees of freedom. And it kind of makes sense because you see, I'm driving this under one parameter. So many of my degrees of freedom are basically slaved to sort of, my driving, okay? And the interesting stuff happens when, the system becomes unstable. So this is really just focusing on the instabilities and where they lead you. Basically subtracting out, all the elastic part of it. Okay? So as you said, this is the limit cycle. So, let me zoom into this limit cycle. And so this is sort of a little more of a zoom in. You start from here, you train up to here, then you go down, and if you trained up to a lower training amplitude, you don't go all the way, you go up here, you return, you land in this limit cycle. So these are a few limit cycles. So let's look at this limit cycle. Yeah? Okay, so this is the limit cycle. So that you see this X is, it's as you increase the strain from O prime to, to the training, you follow the instabilities in the forward direction. You are here, then you return. You are here when you're at minus the training, and then you return here. This is exactly the cycle. You wanted the cycle, you got a cycle. But in fact, you could have said, look, now I'm going to do a readout. Maybe at the readout, I don't go all the way up to here. I go to here. So what happens if instead of continuing with the up arrow, I start to follow the down arrow? And you can do this, and you get this. And now I've placed the vertices here in order to reveal the structure that is there. The vertex placement is sort of in order to really highlight the structure that is there. And the structure that is highlighted is, you see cycles nested within a cycle. This is, okay, so we got much more than we asked for. All I wanted was that the system returns to the same configuration whenever I complete a cycle, or maybe whenever I complete 2 cycles, okay? However, not only did I get the periodic thing, but I got also a whole hierarchy of subcycles. And this is a little bit surprising because, this is not a ferromagnet. And it's not Mahesh's system. There's frustration in the system. And, so, this is sort of surprising. But this is what you get. So you get more than you asked for. And so, you see, I talked about there are hierarchies of nested hysteresis loop. This is what you're seeing there. And in fact, of course, when we go now back to the physics, remember with each of these transitions, there's somewhere in the sample, this is the 2D sample, there's an instability that sets in and triggers them. And what I have done is I've identified the instabilities that are active when you traverse the outer loop. So when you go from X to O, there's a plastic event that takes here. From O to this one, there's 2 plastic events, a mini avalanche that happens here. Then here there is an avalanche of 5 states, the 4 states that is happening here, and you get here. And then when you go down, all of these plastic events have to sort of be undone so that you can return to the same point, okay? And you can have sort of half cycles, but maybe this is for SIT. You see, if you go here, you have basically opened the plastic events in some order, you are undoing them in some other order, okay? Then you're not guaranteed to land in the cycle, you're going somewhere else. So this is a case where the sequence in which you are triggering and untriggering the plastic events does matter. So this is not commutative, okay? And this is exactly a consequence of the frustration. And this is why I've shown this is a one-way transition. Once you transit out from there, as far as you can tell, there's no shear deformation protocol that will get you back into the cycle. Okay, this is kind of like a trap. But this is also a way for the system to sort of escape, okay? And it can, rejuvenate itself. This would not happen in a ferromagnet. In a ferromagnet, you would always be bound to come here, okay? And you would be increasingly trapped in larger cycles until you're sitting in the main hysteresis cycle, and then you're basically doomed for the rest of your life, okay? Unless, metaphorically speaking. Okay, so in fact, I've shown you some of this. In the subcycles, it's only a subset of these instabilities that are active. And so the reason, these instabilities do not have to play nice with each other. This is an example. But what this cyclic shearing does is basically, it creates and it picks up instabilities, it removes instabilities until it finds a set of instabilities that give you this limit cycle. And then it happens to be that they play nice with each other most of the time, where you can, excite a subset of them without messing up the whole system. The mess up here is that, you suddenly bring in a new instability that was not in there, and then it sticks and it doesn't go out, which means you cannot exactly return to the same state anymore. Okay, so this is maybe the take-home of this slide. The mechanical annealing by cyclic shear establishes a high amount of mechanical reversibility. We had seen this already. And in terms of the microscopic mechanics of the system, this corresponds to the emergence of a persistent system of soft spots that can be repeatedly triggered, that do not disappear, and that do not create new soft spots. This, in my opinion, is the process of self-organization, okay? It is the emergence of a persistent set of instabilities that has been selected by the driving. And I'm using selected with sort of, maybe, it has the flavors of an evolution process. If you think about these instabilities like genes, that you get mutated or unmutated or something like this, this is a process. And then you ask yourself, what is evolving? In evolution, you have to have a purpose, you maximize fitness. I mean, and there's various, things that you could put forward as candidates. One of them is, of course, the loss of plasticity or the gain, the loss of dissipation is also something that, Yoav and Itamar have been working. So, this is maybe sort of poor man's in silico evolution, in matter, if you like. So, yes. So memory is the way of encoding these features into the deformation history, which results in the state. Good, and so then, okay, so we've talked a little bit. Is any of this, you see, I'm claiming that this is kind of generic. Yoav can take thin elastic sheets and crumple them, and you get this type of self-organization. This happens in many, many systems. So if we assume this is generic, you're basically getting, this is something that you're getting for free. Does nature exploit it, okay? So the question is, what can self-organization in driven disordered systems tell us about how simple organisms that lack a brain adapt to changing environments? So let's put the evolution thing now to a side. This is sort of a day in the life of a bacterium, okay, who is seeing, various nutrients, temperatures going up and down, competitors coming in and out of its life, okay, and it needs to adapt, without sort of, in a phenotypical way or by changing its physiology or whatever, chemotaxis, neurotaxis, okay? So you see, when we go back, so, the system under cyclic shear, you get a set of persistent instabilities. I think you wouldn't be too surprised if I told you that, if this was under random shearing, you would maybe get something, again, a high degree of reversibility spanned by a set of persistent instabilities. So what you would have is that there would be a section, a set of sort of localized states connected by instabilities that are reversible, meaning that from any state you can go to any other state. This is like here, if you look, you could convince yourself, if I want to go from here to this state, there is actually a deformation path that gets you there. For any pair of states on this thing, there is a deformation path that gets you from there. forward and backwards, okay? And so you assume that this is the same. There are some one-way exits, and you assume, then you see, as your environment is fluctuating, and you look at the system, you see transitions in here. And so what I claim is, by observing these transitions, you have an idea of what's going out. You know, you might not, what's going on outside. You might not have a perfect picture, but you're sampling information about the environment, you know, in this case, a fluctuating strain. So this is really, this is a system interacting with its fluctuating environment that has self-organized into a reversible response. So you've established correlations between the dynamics of your environment and the state changes of your system. And this is a very, in my mind, this is a very elementary kind of, you know, system that can sense its environment. Not perfectly, but it can do something in response to its environment. And this is for me sort of, you know, so this is there. Does biology use it? I mean, I had heard once Marcelo Magnasco sort of say that nature has a criminal mind. It's trying to exploit loopholes, you know. Is this something that could be a loophole for nature is the question. And so here's a quote from Lipschaber and Trusty. The environment and the memory mirror each other. The memory is an internal representation, the state of soft spots in our case, changing states, that proved useful for survival during evolution. And maybe the slogan that I will basically hijack from a paper. So this is generic, as I said. It's a free infrastructure. And so the slogan is self-organization proposes, but ultimately natural selection decides, you know, whether this is useful or not. But I think these are ideas that it may be worth sort of looking into, you know, revisiting old biology experiments to sort of see whether there's any kind of advantage that comes from these mechanisms. I think biologists, by and large, are not aware of these things. We as soft matter physicists are much closer to this. So with this, this is the advertisement for this sort of, you know, this review where this and some other things are discussed. History dependence of microbial behavior. For me, microbes are sort of the simpler kind of organisms than eukaryotes. This is from 2023. Do microbes have a memory? So this is also from 21. So it's also biology is slowly catching, not slowly, it's catching on to it. So with that, maybe just let me show you the collaborators and the funding, and I'll maybe just put out this sort of as the take-home message, and thank you for your attention. Thank you. Thank you very much.
Yeah, Santan.
Nice talk. So with elastoplastic model, when you showed that, like when you are doing this difference, like you have a, like it is coming back to the same previous this thing. Yeah. Yes, yes.
I want to go to the elastic. Yeah.
No. I want that the result actually. Next slide. Yeah. So here, like these are also using elastoplastic model.
Yeah,
right?
this is from the elastoplastic.
Yeah,
model.
yeah. No, so I was thinking that if your rule is similar, then but as you increase the amplitude, so why that return is getting poorer gradually?
There's two things. One of the things that is happening is that actually, you know, this is we are doing a readout after one cycle, but things that Sid and colleagues have also shown is as you're approaching this yielding transition, the response may be periodic, but it may take multiple cycles to return. So meaning that the number of cycles that it takes to return gets longer and longer, meaning that if you just look at where it is at the end of the first cycle, it hasn't returned yet, but perhaps if you knew the period, it would have returned. So part of this is really just due to sort of but we're not sure whether this is just a finite size effect, okay? It could be that this multi-periodicity is just in a very narrow window, but eventually the system does not start to return, and these are averages, which means in your samples, some of them, you know, log still and have a very low value of this. Some, you know, are well beyond yielding and have gone completely somewhere else, and so this is here around, part of this comes from multi-periodicity, part of it comes from, you know, some samples have yielded already.
Okay.
Yeah.
Thanks.
Thank you very much. It's very interesting. So you mentioned at some point that any two states are connected.
Yeah.
Is that in general, or and why is that?
No. Okay. So you know, it's so any two states connected. Actually, so this in graph theory, there's something called mutual reachability. Two sets of stairs states are mutual, in the directed graphs, are mutual reachable if you can follow the arrows from A to B, and then there's also arrows from B to A. Now that is an equivalence relation. So if you can do this with A and B, and you can do this with B and C, then clearly you can do this with A and C because you just go through B and back, okay? And that partitions the vertices into, it's an equivalence relation, and it partitions the vertices into equivalence classes with respect to mutual reachability, and those are the strongly connected components. So that is kind of what I try to suggest here. I mean, from these graphs, you can extract these strongly connected components. You can look at their size distribution, and they are very, very broad. It depends on the annealing state. I mean, so that as well, but they are very broad. But this means anything that has any chance of being reversible has to be confined to a strongly connected component. So the strongly connected component is a coarse-grained view onto this graph. It's a collection of states. I mean, I don't want to, but it's kind of like a meta-basin in this, but, there's no energy necessary, but, in the sense of, mechanical deformations. And sort of these meta-basins, these strongly connected components, their size, how connected they are, how many exits are going out of there. I mean, this will ultimately affect sort of the dynamics, because you see, you are trapped here unless you take one of the exits that goes out there. And if there's only very, very few exits, this dynamics has sort of a channeling, because, it doesn't matter how you got in here, okay? But, once you're here and you're going to leave it, there's only very few exits that you can leave. So there is a sort of, a loss of initial conditions.
Thank you.
There's a question there. Yeah. Oh, yes. Okay.
Any more questions? No?
Yeah, so if there's no other question, then let's thank Muhittin.
Thank you. Thank you. Okay. Do you have the mic on?
Also need that.
Yeah, the dongle for this.
No, it's still the. You're going to try distributing here?
Worked before.
Do you want to keep it here? The connection is better.
Let's try this. No, I think it's yours. Before it worked. Maybe you should switch from this computer to the...
Yeah.
Okay, good. Thank you.
Okay, so next talk is by Yoav Lahini, and he'll be talking about slow relaxations via thermal avalanches.
Yes, thank you. Can you hear me? Thank you very much. Thank you for the organizers for having me here. I will talk about something a bit different than the previous talks. Basically on structural relaxations in amorphous solids and how they come about, what's the mechanism. And I have three underlying messages. One of them is that crumpled matter, crumpled sheets, are a wonderful system to try to observe and probe various phenomena associated with amorphous solids and glassy solids. Second is that the model that was inspired by the crumpled sheets, which I will show you, is also super interesting and can capture a lot of phenomena and also let you probe how exactly things work. And thermal avalanches, which I will explain, is a concept that was, I think, originally conceived in glassy relaxations, but as I will show you or try to convince you, it's kind of general. We see it in our systems, and we think it's more general than that. So these are the underlying messages. And let's start by saying what crumpled sheets are. They are exactly what you think. You take a very thin sheet of plastic, not paper. Paper is a very bad system to work with, but a very thin sheet of plastic, and you crumple it by hand many times until you get this nice crumpled structure. And crumpled sheets have been studied before, but mostly for their complex geometry. Right? So people have shown that there are different building blocks to the complex rough topography of crumpled sheets, that people have looked at the structure of the crumpled sheet when you put it into a ball and have shown that it is fractal. They looked at the structure of the creases and saw all kinds of interesting general distributions and studied how these patterns evolve when you crumple again and again. So a lot of work on the geometry of crumpled sheets, but much less is known about the mechanics or the mechanical properties, although there have been a few works, of course. One of them was actually, if you take a crumpled sheet, a very thin sheet, about 8 microns in thickness. This is the sheet we're going to use in our experiments, and you listen to it. If you've been in the theater and you wanted to open a candy wrap, you know that these things crackle. And people have recorded these crackling sounds and plotted the distribution of intensities of the different crackles and found a polar distribution of intensities. And this is reminiscent of what's known as crackling noise, which is observed in very different systems, driven amorphous solids, distorted ferromagnets, Barkhansen noise, earthquakes. They all have a broad distribution of crackling events, broad distribution in the sense of the intensity of the energy released. Another very interesting signature of underlying complexity is this experiment done in the Nagel group in 2002. Here you take a crumpled sheet and you crumple it into a ball and you put a load, a weight on top of this thing, and you watch what happens. Say you want to measure the spring constant of this thing, and so you want to see how much it contracts under a load. But what happens is something very different. So notice that this is in a linear scale, the height of the load or the volume of the crumpled sheet, if you want, and this in a logarithmic time axis is the time since you placed the load. And you can see that over several decades in time, actually from a fraction of a second to 3 weeks, this thing does not reach equilibrium, and it continues to relax in a logarithmic fashion. That means the relaxation rate slows down all the time, but never actually reaches equilibrium, even after 3 weeks, which at some point you have to give up, I guess, which is kind of amazing, right? So where is the time scale of 3 weeks coming from, and what is going on, and is this some kind of property of the material or some plastic flow in the creases, or is this something more interesting or more, can we learn something about it, right? So the naive thought was, this is a macroscopically disordered system. If it exhibits these kinds of behaviors, can we probe it to understand how things evolve inside? What conspires to give us this kind of logarithmic relaxation. And of course, I should say that logarithmic relaxations are ubiquitous to disordered matter across scales from glassy system, all kinds of glassy systems, to frictional interfaces and granular materials, to even tectonic plates. And you can see them even in living systems and deep neural networks. Slow relaxations, slowing down relaxations are, of course, ubiquitous, and this is an example. At some point, we really were fascinated by this, so we tried to see if we can play with this. So this is an experiment of relaxation under load. You can do the same experiment, relaxation under constant strain. So you strain the system, hold it, and then you see how the force relaxes. This is an aging experiment. And you can play with the strain. After a while, you can change the strain and see how the system evolves. And as in glassy systems, you can see all kinds of memory effects. So the system remembers the previous conditions long after it happens. So this non-monotonic relaxation curve is what you see in the force after the second stage, right? So you compress, hold, this thing relaxes logarithmically, you change the strain, and you can see under constant condition a non-monotonic evolution that carries a memory of previous states. So that's another signature that something interesting is going on. So again, we were thinking, can we use this macroscopic system to understand the underlying mechanics? And will what we find will be general in any way or just particular to crumpled sheets? So a first hint that maybe there is something interesting is in the following. You'll see a very thin sheet. So this is 8-micron thick mylar, which we use in the experiments. And this is a different relaxation experiment. I'm just going to just release it on the table, and you will see how this thing unfolds by itself. And I want you to notice a few things. First of all, oh, there's no sound. First of all, notice that this thing opens up discontinuously, right? You can see that it opens up in jumps. Second, fortunately, you can't hear. Yeah, I did try, but it worked before. Every time there is a, yeah, but somehow the sound doesn't work. Why? There is nothing. Okay, let's see. But every time you see this kind of discrete jumping event, you can hear a crackling, a little snap, a little cracking event. So, of course, you can't hear it now, but believe me, every time something happens, this works. So we decided to do the following experiment. Repeat the experiment I showed you before. Take a crumpled sheet, crumple it into a ball, put a weight on top of it, and watch how how the volume logarithmically decays over time, right? So the red curve here, linear axis of the height of the weight, logarithmic axis in time, only up to a day. We didn't have patients for 3 weeks. And you can see this logarithmic compaction of the crumpled sheet under load, right? I reversed the directions for a reason you will see before, but this thing is the displacement as a function of time. It slows down, and you can see that it goes very nicely logarithmic. But now we also listen to the underlying evolution, underlying crackling sounds. We don't know exactly what it is yet, but we can record the crackling events, right? And for each 2 crackling events, I can measure the time delay between consecutive pops, right? And I can draw them on the same graph. So in blue here, you see blue dots. This is a log-log plot. So the waiting time between consecutive crackling events on the same time axis as the height data, right? And this is the kind of data you get. I'm going to dwell on it a little bit. So you see a few things. First of all, at very short times, when the system is young, let's say, the time between crackling events is very short, 1/10 of a second. After a day, the time you wait between crackling events can be an hour, right? You can wait for an hour, nothing happens, and then you hear something. And this whole thing grows linearly, right? The time between consecutive events, on average, or the cutoff grows linearly with the time since I began the experiment, right? That alone can give you logarithmic relaxation if the relaxation timescales grow linearly. But there's a lot of structure under here, right? And specifically, if I'll zoom in, so I'm zooming in on the time axis, and you see this is the cutoff that grows, And this is the waiting time between events, and you can see these vertical streaks. What are these streaks? Any guesses? These are avalanches, right? These are many events happening at a relatively short time event, and they are spanning. There's a special avalanches. We'll talk a lot about these avalanches, but these are avalanches in which many events happen in some correlation, in some correlated fashion, right? And you can notice this every time you have an avalanche, you have a step in the relaxation curve. Big avalanche, a big step. Small avalanche, a small step. The crackling dynamics indicate something that is driving the relaxation of the system. Is this clear? Yes.
Can you look at, oh, sorry. Can you look at, you can measure kind of the size of the avalanche by counting the dots? Can you
Yes.
correlate it to the step?
Yes, absolutely.
Okay.
Yes, yes.
Why are they?
Yes, the number, so the energy released in this thing is hard to measure for various reasons, but if you just look at the size of the avalanche in terms of the number of crackling dots you hear, it's linearly proportional to the size of the jump. This is why we're saying that this crackling dynamics indicates the thing that kind of drives this relaxation. Yes?
They're also kind of equispaced.
Well, that's, yeah, someone told me that already. I think it's just a fluke of where I zoomed in. It's not supposed to be spaced.
Oh.
But I agree that I should take another section. Yeah.
So
Yes.
yeah. I mean, so each dot is like
Each dot
a micro
represents the waiting
event.
time, the waiting time between a popping event and the previous one. Just how long you waited, or 1 over the rate if you want, 1 over the instantaneous rate.
Okay. So, but the whole thing is one avalanche, is what?
The whole thing, I'm going to call it an avalanche.
Okay.
But you can already notice that this avalanche is kind of weird because it spans many time scales, right? It's not a domino avalanche. It has slow things and fast things, but they're all correlated. So this is the thermal avalanche that I'm going to hopefully get to. Okay, yes? Sorry, again?
There's a set of papers over a decade by Edward Vives and
Yes.
Planes.
Yes?
They had, looked at this kind of avalanche dynamics in many systems,
Yes,
including
but actually I
Martin
was talking to
sites.
Vives, I'm not sure. So I will
Okay,
be happy
we
to
can-
see, but
yeah,
I'm
yeah,
not sure
yeah.
it's... all right, so this now motivates us to understand the mechanics. How much time has passed? 10 minutes have passed. Okay, good. So this motivates us to try to understand what is the mechanics of crumpled sheets, what gives rise to these popping sounds, and can we connect the things in order to understand what's the mechanism driving this thing, and why do we get this, and is this really the thing that drives this relaxation process? So the mechanics of crumpled matter, the experiments are super simple. The first experiments, you just take a crumpled sheet, in this case a thicker sheet, just to visualize things much nicer. So you have a sheet. At one edge of the sheet is connected to a linear stage that can compress and decompress the sheet, right? The other edge is fixed, but it's connected to a load cell or a force sensor that can measure the resistance force of the sheet as a function of the displacement, right? But because it's a macroscopic system, you can also 3D scan the sheet in order to see what happens to the sheet itself when it does what it does. And you can, of course, listen to the crackling sound. And you can correlate local observables with global observables and try to understand the mechanics of the system. If you just look at the sheet when you stretch it, again, I'm sorry you will not hear it, but you will see it. I'm just stretching, and you can see, oh, there's a little bit of sound. Hopefully, you can see that the surface is active, right? Things are happening as I compress and decompress the sheet. Things are popping in and out, and maybe you can spot an avalanche or two. So, but the measurement itself, so I'm measuring the normal force measured here by the low cell as a function of the displacement, and I see this kind of curve, overall rising, so the force is rising overall, but there are a lot of stress drops, right? Which should be familiar for anyone who ever sheared an amorphous solid experiment or simulation. And if you look at this force drops, we can, for example, look at the distribution of sizes of drops just to see if it's broad. And it starts to look, it's a decade and a half. I wouldn't call it very broad, but you see that there are many different sizes of things. So now we can ask, okay, what are those stress drops? Right? We kind of correlate the stress drops to the drops in the relaxation curve, right? So what are those stress drops? So I can drive my motor just to a point where I see one stress drop, right? And then start oscillating around that just to see what that creature is. And what I get is something that looks like this. So I get a small hysteresis curve with two states, basically. This thing has an elastic response. At some point, it jumps up. Something jumps up. If I go back, it jumps back to the original state. But there's a difference of threshold between the jump up and jump down. And in the literature, people call that hysterons. So a two-state hysteretic degree of freedom. So each one of these stress drops is one of these two-state things. If I 3D scan the sheet to see what happened before and after the stress drop, I can scan before and after, subtract the two images, and see what changed in the sheet before and after the stress drop. I see a very localized event. You've seen it in the movie. Something popped in and out of some facet in this crumpled sheet, popped in and out of the plane. And this also produces our familiar crackling sounds, right? So each crackling event that we measured is actually one of those instabilities popping. That's what we got. Good. It's easy to show that these bistable things interact, right? It shouldn't be surprising. They're in the same sheet, so a bistable thing that pops in and out can affect the threshold for popping of a different bistable element in the sheet. So this is it's very easy to measure. You locate two instabilities, right? Two of the things that pop in and out, and you just take one of them and pop it, and you measure the force, right? You come from the side with the probe, you push, you push, you push until it pops, and you see at what point this thing gave way. That gives you a measure of the threshold of this thing to pop. And now you repeat the same experiment, only before you flip that one, you flip a neighboring guy, right? So this guy was down, now you put it in an up state, and then you measure again, and you see that the threshold has changed, the signature of interaction. You can see that there are positive interaction and negative interactions. And there's a lot of complexity. So that gave Daniel Hexner an ingenious idea of how to model our crumpled sheets. And the model goes like this. It's a two-dimensional network of springs. It's a random network of springs. The springs, though, are bistable. They have two states. They can be long or short, right? They have a double well potential. Basically, you have a spring, and if you pull on it only slightly, it acts like a spring. It's elastic. But if you pull on it enough, it can jump to a long state and then become a long spring. And they can, of course, go back and forth between them. All the springs in the network have the same potential, except for one thing. The average rest length, right? Each spring has two rest lengths. The average rest length is randomized, just to add some disorder to the system. But the barrier, the depth of the wells, the symmetry, everything is the same across the system. And of course, the topology is random. And that results in a network that's highly frustrated. The reason is very simple. The rest lengths of the different springs are incompatible, basically, right? So there's a lot of stress in the system that the system cannot get rid of. The color indicates the stress on each one of the bonds. That means that bonds generally deviate from their minima. That means that you have, well, that gives rise to a lot of stuff I'm going to show. Questions so far? Yes.
So in the previous slide, when you are showing the density of deformations, the second figure. So how are you measuring that? Are
3D scanner.
So
a 3D scanner.
Okay. So basically, it's just the image. You are looking at the image, and
it's a height map.
Okay.
And you can subtract the height maps at two different states and see the difference, see what changed. All right. So just as a first check of the model, we take, Daniel took his model and just periodically decompress and compress it to see the response. This should remind you of what we saw in the crumpled sheet. You have localized instabilities, but they sometimes group into avalanches or small avalanches, fast avalanches. And this is the strain stress curve that you get when you do periodic compression and decompression. And here you see a lot of stuff that I skipped because I don't have enough time to tell you. But there's a lot of interesting stuff going on. For example, adaptation. I don't know if you can call it like that, but the first time you do something, the system goes crazy, snaps all the way. The second time is much smoother. The third time is even smoother. And the system converges to a limit cycle that minimizes dissipation, basically. And this is what happens here. When it converged, there are memory effects, which I did not tell you about, but we have a lot of work on memory effects. Sorry? And one of the interesting insights here was that although all the springs are identical in the network, if you look at, just a second, if you look at the distribution of, don't scare me. If you look at the distribution of stress drops, it is very broad. Again, all of the springs are identical, but the distribution of stress drop of the whole system is very broad, and that is due to the inherent interactions, right, to the pre-stresses. Most of the springs, or many of them, are very close to instability. You don't have to push them a lot. That gives you those small edges, and these are avalanches, so you get broad distribution just because of frustration, not because of variability in the bonds themselves. Yes. Well, seems like it.
Just very minor clarification. So you're not actually rearranging, right? You're just snapping back and forth. So your bonds, no bonds change?
No, the topology of the network is fixed. Yeah. But bonds get long. And actually, there's a lot of stuff that I'm not telling you. Bonds get long. The interaction between bonds changes because of geometric effects. You can get non-pairwise interaction. All kinds of funny stuff happen because of the topology of the network and because the topology is fixed.
So yeah, I'd like to chat.
Sorry?
I'd like to chat eventually.
Let's do it. Okay, good. So now we have an understanding of the mechanics of crumpled sheets, and we have a model that seems to capture very nicely, although I didn't show you the experimentals that go with it, but captures very nicely a broad range of things. The hysterically sprung, the broad distribution, the memory effects, the cyclic memory effects, and everything. Is this enough to explain this slow relaxation phenomenon that I've shown you, or do we need some other stuff? So crumpled sheets are a frustrated network of instabilities. Can this kind of explain this phenomenon? So we took Daniel's model, and we implemented in the lab a molecular dynamic simulation of this model. I'll tell you in a second why. But basically, we take the model as it is, and, sorry, the colors are different because it's a different engine. Daniel was doing energy minimization by steps. We did molecular dynamic simulations, right? So the nodes here are small masses, but they are connected with bistable springs, right? So you have a network of bistable springs. And the color indicates how close you are to instability. So you see some of them are very close to instability. And you can add temperature to this thing and see what happens, right? That's the only thing that's changed. So we take this model, we put it under external load. So we put forces on the edges. And the system collapses. At zero temperature, the system collapses a little bit under the load and stops, and nothing happens from that point on. And then in the simulation, we excite a little bit of temperature. How much is a little bit? If this energy barrier is, say, 1, we're talking about 10 to the minus 4. Right? So a very, very small temperature, which shouldn't really do much. And now I'm going to show a movie of the dynamics of the system. You can see what happens. And basically, for a long time, nothing happens until at some point, there's an avalanche. And then again, nothing happens. Here is the compaction of the system, another avalanche. And now you have to wait much longer. I'm going to skip it, much longer to see the next avalanche. So you see that the system compacts, but it compacts in steps, not continuously. And the steps, the time you have to wait between steps gets longer and longer. And each step is actually an avalanche of many things that happen during things. So if you look just at the area of the network as a function of logarithm of simulation time, you see a logarithmic compaction, but in steps. If you look at instabilities during this relaxation, you can start to see this linear slope of waiting times between events and these avalanches. And if you simulate a much larger system, you get many more avalanches and a smoother curve. And now you can look at the size distribution of the avalanches, and you find, somehow I don't remember showing you the size distribution of the avalanches in the experiment, but it looks exactly the same, right? So more or less m to the minus 2. So m is a measure of the size of the avalanche, just in the number of events. And if you just plot a histogram of the size distribution of an avalanche, you get a power law with m to the minus 2, more or less, both in the experiment, which somehow got mixed in the presentation, and in the simulation, right? So simulation captures the slow relaxation process that I've shown you in the experiment without adding anything. It's just elastic bonds, a little bit of noise, but you don't need the material creep, you don't need anything. This just happens from frustrated instabilities kind of driven by noise a little bit. Okay? How much time do I have? 6 minutes, okay. Okay, we'll have to choose. What? Yes, somehow, I don't know where it's gone, but yes, I should have shown you. Right, the first thing you do if you see avalanches, you measure the size distribution and try to show that it's earthquakes, so yes, it's earthquakes. Yeah. Okay. Okay, I'll try to speed up. Maybe I'll skip some of the part. Okay, so we're trying to understand what happens, for example, in one of these plateaus. You've seen that I can wait a long time until something happens. Nothing seems to happen, but then at some point, you get an avalanche and a step in the compaction. So what's happening here? What's the process, or what's going on? So it's easy to show that you start, right, you do many simulations starting from the same point, the initial point of the plateau, but you do an either configurational ensemble, meaning you're running many simulations of the same system with the same temperature, but different realization of the thermal kicks, and you can get statistics for this event to happen. Of course, you choose only the case in which this event happened and nothing else. More about that later, but you can get statistics of how much time you have to wait before this thing happens, and you get an Arrhenius process, right? So there's a single energy barrier that kind of blocks this thing from happening, and that energy barrier grows as the system ages. You notice that when you start, it's very small, right? The single spring has a delta U of 1. And here we start with something that is 0.05. So the initial energy barrier when a system is young is very, very small. And that energy barrier that kind of blocks you from the next step grows logarithmically with the age of the system. And that gives rise to the slowdown of the whole process, right? The first energy barrier you have to go in order to initiate the avalanche is very small. The next one is slightly bigger. You have to wait longer. And this is what we get from the simulations. Yes. Sorry? So just from the statistics of the waiting times to activate, I'm running many simulations with the same temperature, different realization of thermal kicks. I get statistics of how long I have to wait to kick it. And from this, I can see it's an arranged process, and I can estimate the barrier height. Yes. Maybe later. Okay. I'll skip this. Well, okay, I'll skip this. We can look at the model and try to see what the spectrum of states are. Who are those very, very small energy barriers? So we can look at the spectrum, basically by looking at the Hessian of the system, and we find that there is an excess of soft modes with very, very low energies at the bottom of the spectrum. They have, well, it's not a lot of data, but they have something that looks like omega to the fourth, which is known from simulation on glassy systems that they have these excess modes. Each one of these excess modes is actually an instability very close, just because of the some instabilities are very close to the threshold. It's a very soft system, and you have a quasi-localized soft mode around it. So this is, again, very similar to things you see in a simulation of glasses. We try to understand the slowdown of the thing. This is work with Mathieu Huillard, and I will skip it because I don't have time. But the idea is, I will not skip it. The idea is the following. The system self-organizes into a marginally stable state. All the springs are pushing each other. They are incompatible. They're pushing each other. And we have shown together with Daniel Hexner and then together with Mathieu that the system self-organizes into a marginally stable state. That is, the energy barrier is close to zero, is flat. You have a macroscopic, you have a population of states at almost zero activation energies. And as time goes by, there's a gap opening in the lower edge. That means that the lower edge of the system is, the lowest energy barrier grows a little bit, and we explained how in this work. The avalanches occur here. So we are at very low temperature, right? So we are talking only to the lowest energy barriers in the system because we are at very low temperatures. And when we excite one of these things, they can kick others into the gap and out of the gap, so we can create more unstable things. And these are the avalanches that occur. And we have an analysis of this in this work. So thermal avalanches, give me how much time? 4 minutes? Good. Thermal avalanches, I'll give you the gist of the idea, and I'll skip the analysis. The thing is that usually when we talk about avalanches, I don't know if it's usually, but when we think about avalanches, you think about domino effects or immediate avalanches. One thing destabilizes the next, and these things runs as fast as the speed of sound. Here we see that each avalanche contains many timescales. There are very slow events and very fast events, and if you looked at the movie before, you saw it also happening. The gist of the idea is this. Instead of each event just getting a kick and getting destabilized, what happens is that when an event pops, it kicks another bistable spring, and that spring doesn't immediately pops, but the energy barrier for it decreases dramatically, right? This is a facilitation effect. So a bond popping can lower the energy barrier significantly of other bonds, and now they are prone to thermal activation, right? And this can happen after a finite, but could be a long time, right? And this is how you get slow events participating in the avalanche.
What is the equivalent of temperature?
Good question. Just noise. We can increase it just by adding vibrations, so just acoustic noise. I don't think it's temperature. Okay, the analysis of this gives you a prediction for the distribution of waiting times within avalanches. Should go like, so the distribution of waiting times here should go like 1 over delta t, and we saw it in the theory and in the experiments. It fits very, very nicely. So this is the signature of thermal avalanches. They have a funny shape, these thermal avalanches. So now I'm zooming in on one of these thermal avalanches, right? And this is the background rate. And at some point, you see this thing accelerates, gets to the core of the avalanche, and then decelerates back. And it's interesting. I don't know what to say about that, but this is a generic feature of the avalanches in our case. In crumpled sheets, yes.
I mean, to the left and the right of T0.
Yeah, I mean, on average, it's hard to, but yes. No, not in our case. We are playing with this now. We're trying to understand if this is, but yeah, it's a good question. But so far, yes. Okay, I need to wrap up. I think we analyzed a lot this thermal avalanche. It has a very interesting spatiotemporal hierarchical structure, right? So a single event is waiting for a thermal kick that will kick it. This kicks a fast cascade. So this is a domino effect, a cascade. The cascade changes the potential for other events and then thermally facilitates other cascades. And you can see a really interesting spatiotemporal hierarchy of these thermal avalanches. And it's interesting to note that it's very similar to the hierarchy, the spatiotemporal hierarchy that was observed for dynamic heterogeneities in glassy systems. You can look at that paper. It looks very similar. Of course, similar doesn't mean much, but it looks very similar and maybe hinting at something interesting. Just a point about this isoconfigurational simulations. We start at the same initial state, right? And we run the system the same model, the same realization of the model for the same temperature at a different realization of the thermal kicks, right? So we create replicas, and we want to see how these replicas evolve and how the distance between them evolve. This can be used to kind of characterize the energy landscape of the system. So what we see is that the distances between replicas, you can define a distance between the states. It is a function of time. The distance between replicas grows and is Gaussian. Basically, on average, it grows. And if you look at the distance metrics, you can see a complex structure which has a flavor of, well, I don't want to say replica symmetry breaking, but it has a flavor of complexity in the energy landscape. All right, one last minute, just to show you that this may be more generic than crumpled sheets. Omori's law for earthquake aftershocks. So after a big earthquake, there's a series of aftershocks. And there's a famous empirical observation that says that the rate of aftershocks after a big event decays in a certain way, the rate, right? So the rate goes like 1/T, right? Or the waiting time between consecutive aftershocks grows linearly in time since the main event. And so this is just for data for a certain earthquake, and you can see this decay. So this empirical law fits data very nicely. And this is the same data for our crumpled sheets, right? The rate of events, on average, decays in the same way. But of course, we've shown that underlying this slowdown, there's a lot of funny stuff going on, thermal avalanches and this. So the question is this somehow evident also in the aftershock data? So we took aftershock data, and I'm just going to show you a picture. So this is the crumpled sheet data, time versus waiting time between events, and this is aftershock data from a big earthquake in 2019. This is time since the main event. This is waiting time between aftershocks. You can see Omori's law here, and you can maybe see some stuff going on. We are currently running a lot of analysis, and the statistical similarity between of these cascades, the waiting time between cascades, the distribution, the shape of everything looks very similar. But again, looking similar is not, but it's interesting, I think. So maybe there's hope that this is more general. All right, just to say thank you to the people. Dov Shochat is the graduate student who ran most of what you've seen, a very talented person. Keep an eye out for him. He's now doing a postdoc in Amsterdam. Yaniv is a master's student in Negev, is an undergraduate who did a lot of work on the earthquake. Vladimir is our simulation guy. Daniel Hexner, Mathieu Weert, and Daniel Korczynski were our theory in what I've shown you, and stuff I did not show you, but it's very interesting. It's on the archive. It was done together with Martin Van Ecke, Paul Bakerner, and Itamar Prokacha, and that deals with a system that ages, like our crumpled sheets, but then it's subjected to cyclic driving. So it ages while it's being subject to cyclic driving, and we find another seems to be very general phenomena, and we explain it with our model, of course, and it's also very nice work. So that's it. Thank you very much. Which phenomenon? Well, what you see is across different experimental systems, we did a few different systems. What you see is if you look, you do a cyclic shear and you look at the hysteresis curve and you measure the area, which is basically dissipation. So you see that if a system ages under static strain, under cyclic strain, the area or the dissipation per cycle decays logarithmically with the number of cycles. And that is generic across different systems. And we compare different models that capture logarithmic relaxation under static strain. So there are different ways of explaining that. And we tried to use them for the cyclic phenomena, and all of them failed except our network model that kind of captured it. And we kind of say what's going on.
Okay. So, the spring network system that you have is a very appealing model for a lot of disordered matter, but I want to ask if it captures in the same way that glasses do the phenomena of failure or yielding and annealing.
So the annealing is something we're going to do. definitely there is something, it depends if you, annealing you mean under cyclic or?
No, in general, the idea that
Yeah,
you can have
quenching
different degrees
or
of
annealing.
disorder and
Yeah,
so on.
you can see stuff, but this is work in progress. As for yielding, we're not allowing anything to break here, so I don't think so, right? But I can tell you that we're doing a lot of simulations on this model, and we capture other stuff. There is something that looks like a glass transition, a Gardner transition. A lot of stuff is happening in this relatively simple model. But of course, there's a difference. The topology is fixed, and I don't think you can get flow or anything like that. Who's asking?
Who is
Yes.
asking?
Is the topology of the network also randomly generated, or is
Yes, yes. So it's derived from random packing, far from the jamming transition. It doesn't seem to matter too much.
So if I had a lattice and I just randomly generated
lattice is the one thing you shouldn't do.
Okay.
But anything that's slightly random generates everything. It doesn't really matter, right? Even, for some reason, it just happens.
The degree of randomness also doesn't affect.
As far as we saw, we didn't explore it too much, but as far as we saw,
because it should affect the amount of frustration
yeah,
in the system, right?
I basically agree, but if you take a reasonably disordered configuration, it works.
Sayantan?
Great talk. Yeah. So since you have like broad distribution of avalanche time, so as thinking that have you looked at the rate dependence dependent of your cyclic shear? Because I was hoping that if you do it fast, some of the it can evolve.
So the slow avalanches we don't see in the cyclic shear. We see them in the aging experiments. During cyclic shear, you get fast avalanches. At least in the experiments we did so far, which are athermal basically because the sheets are thicker. So we didn't really explore what happens with very thin sheets under that, and I don't know.
But if you vary the rate considerably, let's say by 2 orders of magnitude,
Sure.
it should, how it approaches limit cycle, it should change.
Absolutely, but we did not do it yet. Of course we should, but we didn't do it yet.
Thanks.
Yeah. So, one hears of the 4 warning shocks, right? The 4 shocks.
Yes.
I don't see anything about the statistics of those. I understand that they are very unpredictable, but
we are talking to some geophysicists about this. So in the community, as far as I understand, there are claims that there should be 4 shocks as much as aftershocks, but for some technical reasons, they are very hard to detect because there's noise before or whatever.
it's probably also difficult to guess when you
Yes,
start.
yes. In the data, right, if you consider, basically, if you look at, our experiment, the analogy to earthquake is that the beginning of the experiment, when we put the load, that's the main event, and then we have, but you can look at these cascades as secondary events that create their own Omori tail. And in our experiments, it's symmetric. We have foreshocks and aftershocks together. In the seismic data, not so. Although everything else looks very similar, the shape is not, yeah, there is something there, and yeah.
Okay, so if there's no other question, let's thank you once more.
Thank you.
And let's have a short tea break, and let's meet at 3:50. 3:50.
So starting just now, okay, the risk is less that Uber will cancel on you. So we have a corporate account, so it's right downstairs in the reception.
This is on top of the time that we gave for departure?
No, this is different.
Different.